Okay, as you can see here, the area between the curves, suppose we're computing the area enclosed by the red area here and the blue one from the interval from A to B. Okay, the formula it will be the integral from A to B of the absolute value change, absolute difference of f and g. In a special case where g is equal to 0, it gives us the area under the curve here of f. That is for the area, right? You can think of this way. The area will be dx here multiplied with the length, right? The length here from G to F will be the difference of these two. Okay? Do you all see it? That is all about the area. Okay? And the Riemann sum, when we discretize the domain into finer and finer rectangles, it will come closer and closer to the real area of this one. So in general, the area enclosed by the function f and g from the interval from A to B, suppose f is larger than g, then it will be the integral from A to B of the difference. Okay? In general, the area of any function will be enclosed by any function will be the integral from A to B of absolute value of f and g here. Okay? Sometimes the curve, there are some intersections. So our job is to find them if there are some or any. If we can find, for example, we're given the curve f is the red line here. The g is the green line, a blue line here. Then, according to this figure, what we need to do is to find the intersection point here. And we study in each interval whether f is larger than g or g is larger than f. If we know specifically, we can get rid of the absolute sign here, right? Then compute the integral easily. That is all about the area in section 6.1. So do you have any question for me? Yeah, very good. It will be similarly if we are computing the area in the y direction, for example. Oops. We will do it when we see a specific case. I think it's easier. And about the volume, the section 6.2, we study how to compute the volume, right? Suppose we are given an object here. Let us look at this one. If we slice this object in the direction perpendicular to the x-axis here, it will give us the area AX, right? If we compute the integral from A to B, and at each position, x star here, we can compute the area of A, then the integral will be the sum of them, right? And finally, it will give us the volume of this object. Okay. The same story. If we slice this object in the direction that perpendicular to the y-axis, then the integral will depends on the y variable. So, as you can see in the notes here, I gave you yesterday. For people at home, you can download it on Moodles. Okay. So you can study one example deeply, and this is given here. If you want to compute the volume of an object that is rotated about the x-axis, right? And you can see in the figure 1 here, if it is rotated about the x-axis, we slice this object, right? Perpendicular to the x-axis, it will give us the circles, the inner circle and outer circle, right? Then integral, so if it rotates about the x-axis, then we take the integral from A to B in the x direction. And the area we need to compute will depend on the variable x here. The same story. If we want to compute the area of the volume of the enclosed area here, rotated about the y-axis, right? It means we need to slice this object in the direction that is perpendicular to the y-axis. Then we take the integral from C to D, right? Where C and D are the upper and lower limits in the y direction. But now the area will depend on the y. At each position of y, there is a circle here, right? 2 circles. Then doing that, we can find the volume of this object. Okay? That is the section 6.2. That's it. But now sometimes we face a difficult problems like this one. We use the method called cylindrical shells method. In that method, you can imagine this cylindrical shells, the very simple object here. And you can derive this, and the volume of this one will be the circumference times the thickness, delta R, where delta R is this here, right? And the height of the cylinder. Okay? So look at this function. This is a very good figure given in the slides. Suppose we're given the function f of x here is this curve, right? In this region, the thickness is this distance from xi minus 1 to xi here. That is the thickness, or delta x here. And the height of this one is exactly the difference and the value, the distance from the x-axis to the function f of x here, right? And the formula of that is 2 pi x multiplied with the height, which is the function f, dx. In this case, the variable will depend on the x variable. Okay? Look at these figures. Try to memorize it. Okay? If the delta x is smaller and smaller, it will come closer and closer to the real volumes of this object. Okay? When we're at home, spend more time to look at these figures. And we have done some example. Yeah, and this is the way how we can remember this formula. Suppose you cut the cylinder here and stretch it. Okay. Then the length of this will be exactly the circumference of this circle here, 2 pi x. Thickness is dx. It is here in the left figure. Fx here is the height of the cylinder. And this dx is simply a notation of the integral. Okay? In Riemann sums, it will be the thickness, right? That's it for the section 6.3. Okay? Yeah, we review many things. And here is the first example we've done together. Did you compute at home and check if it is the same as here? 16 pi over 5. Yeah, if you haven't, try to redo it. Okay. This is the object when it is rotate about the y-axis, right? Then we use the cylindrical shells formula. How about if we rotate this enclosed area here about the x-axis? What is the formula for the volume of this object? Hold on a second. So if we rotate about the x-axis, right, then we slice this subject in the perpendicular direction. And each slice will give us a circle like this. So at each position here, it will give us a circle like this. Okay. And our job is to find the area. So what is the variable in this case? And what is the upper and lower bound of this integral? Very good. From 0 to 2, right? Because we slice this in the direction that is perpendicular to the x-axis. So we see that the variables depends on x. This is dx, right? At each position x here, we need to compute the area of the circle. That depends on the position x here. Okay. And this area is a circle. And what is the radius of this circle? Perfect. Do you all see it? Where the area, the radius depends on x. And r of x is exactly f of x here. The radius is this guy. Okay. The computation is not hard, but the imagination is, yeah, we need to do it more. Okay. So it depends on the problems we choose which method to use. And again, these problems, we can use the cylindrical shells formula to compute the area, the volume, when this area is rotated about the y-axis, right? And again, from the cylindrical shells formula, this area is rotated about y-axis. We take the integral with respect to the x variables. Right? And at each position of x here, we draw a circle around the y-axis here. So the circumference of that would be 2 pi x. The thickness is dx. And the height will be the difference of this line and this line, which is this one. Okay? That is all about cylindrical shells. I think today we'll do, sure. This one? Okay.
So when the radius is going perpendicular to the y-axis, we use dx. And then when it's going perpendicular to the x-axis, we use dy.
I'm sorry. This one we applied the formula in the section 2.
But since that's not a cylindrical one.
No, it's not. Yeah.
So whenever it's cylindrical, that's when we have to worry about dx or dy.
We also need to worry about that. But here, they're a little bit different. Here in the section 2, the washer, the dish formula, if we slice this perpendicular to the x-axis, and the variable is the x, right? But the cylindrical shells, there's a little difference. You're right. We should be careful about this. If, yeah, here, let me go back to the original one here. If we slice this, it rotates about the y-axis, right? In the previous section, if it rotates about the y-axis, then the variable depends on y. But the cylindrical shells is a little bit different. We rotate about y-axis, but the variable here depends on x. Yeah. Just memorize this figure. It helps you to recover the formula. Don't be confused between these two. Okay, how about, okay, let us do this one. Suppose, interesting. Sorry, you know what? Okay, suppose we're computing the cylinders that is if we're given a cylinder in this way, right? And the thickness is like this. Oops. Okay. The thickness here is d in the y direction, right? And the height, let us compute. This is the height. Right. I think it's better if we draw it from 0, easier to see. Here. So the volume of this guy, right? Now we slice. If it rotate about the x-axis, right? The volume of this guy, the similar story. It will run from A to B, but now yeah, let us call it from here to here, C to D here. Okay. The variable will be depending on y, right? dy. And if we slice this, the thickness of this guy would be in dy. And what is the height of this guy? Here, right? It will be a function in the y direction. And the same story at each circle here will be 2 pi y, right? circumference of this. Okay. Now let us do one more example. Find the volume of the solid obtained by rotating the region bounded by the function. The curve y is x minus x squared, and y is equal to 0 about the line x is equal to 2. X minus x squared. We can draw a graph of this guy, right? So what is the x-intercept of this guy? Very good, 0 and 1. Thank you, Carson. 0 and 1, right? What is the maximum of this guy? The maximum value will be at 1/2 here, right? Very good. Okay. As you can see in the section chapter 5, you can draw a graph of this guy. Maximum here at 1/2. So y at 1/2, it will be 1/2 minus 1/2 square here, which will be 1/2 minus 1/4 multiplied by 2 divided by 2 give us 1/4, right? 1/4, it will be here. So we know the graph here. And the y-intercept is at x is equal to 0, which is 0, 0 here. Maximum is right here. Okay. The highest degree of this guy is negative x squared. When x goes to negative infinity, it will be negative infinity, or positive infinity is still negative infinity. So, and it is concave up and concave down, or you can study all these things. And finally, you can draw this graph, and we call this guy is f of x. This is the function f of x, okay? And where is the line y is equal to 0? Yeah, the x-axis. Very good. This is y is equal to 0. So it means that the area we are looking for is this guy, right? But then the area here is rotated about the line x is equal to 2. Wow, interesting. X is equal to 2. is this guy. Okay, it rotates about this guy. So, do you all see it? So, suppose the line here okay. This guy will be rotated, and when we rotate about the x is equal to 2, it will draw a circle here, right? Okay. Look at this. Can you imagine it in your head now? If not, continue looking at this until we understand how the object looks like. Do you all see it? Cannot? Okay. It's hard, right? I agree. Suppose the area is this guy. The x-axis is horizontally here. The y-axis is perpendicular. This is the line x is equal to 2. It rotates about the x is equal to 2. Do you all see it? Okay. It's hard, yeah, take your time, no rush. And when we rotate it about the x-axis, at each point on the curve here, it will draw a line in purple. Okay? And if we consider the point at the bottom of this guy, it will draw a green, yeah, it's not symmetry as I draw, but you can imagine it, right? It will draw another circle, green circle here. And the height of this cylinder, right, is the distance from the x-axis to the curve here. Do you see it? Think about it. Yeah, spend more time on this until we understand all of this. Okay. So we have the figure here, and the way we compute to get the graph, let me pull it down here. Okay. Now, the same logic, the volume, right? We use cylindrical shells. The volume will be the integral we rotate about the x is equal to 2. It's similar to the y-axis. The y-axis is x is equal to 0, right? So the variable here, the thickness, depends on x. Okay? So this integral depends on x, has a thickness here, depends on x. Okay? And the same story here will be the height of and the circumference here. Okay? Circumference will be 2 pi r, where r is the distance from the point here to the axis where it rotates. In this case, it's x equal to 2, right? Okay, which is the distance here from any position x here. If the x point is right here, then this is the distance. Okay? And the height of this guy, what is it? It would be the distance from the x-axis to the graph here, right?
So 1/4.
Say it again, please.
1/4.
Yes, very good. That is the specific point here. But in the general point, the curve here satisfying the equation x minus x squared, right? Do you agree? So the distance will be from the position on the line here to the x-axis, which is x minus x squared minus 0. Do you agree? That is the height. If you don't agree, just say it out loud and think about it more. Right, the distance from here, the height of the cylinder here. Yes. Where is it? The bottom here?
What is R?
R here. R is the distance. R is the radius from the origin to the point we're considering here. Here, look at, yeah. The same story here, you see? Their cylinders, it rotates about the y-axis here, okay? And the formula is 2 pi x, where x is the distance from the center to the middle point of the cylinders here. And this is R in this case, which is x, right? Okay. In our case, the distance from the center of the cylinders is this guy, right? So if for any position here at x, what is the radius from x to 2 here? Very good. 2 minus x, right? the radius is positive and x between 0 and 1. So 2 minus x is always positive, so it makes sense. The radius is not negative. If you do x minus 2, it will also give you the difference, but it's negative, right? So therefore, in other words, this guy becomes 2 pi 2 minus x times the height, in this case is x minus x squared, and the thickness here is dx. Okay. What do we need to find?
So does like what the function that we use for the y, does the negative x matter when it comes to x formula? We could just have x minus 2x minus 2. But the y function is negative x minus x squared. Oh, that's fine.
Yeah, it's fine. Okay. So when we ask a question and we realize something is good, it happens to me and to everyone. Sometimes we was about to ask, and when we speak it out loud and we understood it, immediately write that. It's fine. It's good. So what do we need to find? The upper limit and lower limit here, right? You see? It starts from here to here, right? So we need something like that. That is the upper limit and lower limit. It runs from 0 to 1. 0 to 1. Is it clear now?
So when finding this, we always use the original function, like where we're finding the area.
I think the best way is to think about it more, right? And do many more problems. But do each problems clearly and understand it deeply. It will help you to apply many other problems. Don't, yes. 0 to 1 because the region here is enclosed from 0 to 1, right? So now it becomes an easy integral. You can do it easily. And you can double check it at home. It will be pi over 2. Okay. How about if we rotate it about the y-axis, right? It becomes an easy problem where r here is simply x, right? And the same story applies. I mean, the only things difference is the distance, the r, the radius. So just go home and do it again. Oh, one more thing. The test 4, there's a typo. I have already updated on Moodle's test 4 review. In the question, yeah, you'll find it about this stuff. Okay. I'll see you tomorrow. Oh, one more question. Sorry, but do you want to take the test on Friday or next week? Okay. So that's it. You have a good one. You too. You're welcome.